Thank you, Hal. Thank you for coming. So I will talk about something which is very old and classical, but with a new spin on it. So I hope you will find it interesting. Not so much geometry, so I apologize for that. So it's sort of famous that the Ising model has Pfaffian correlations. And the idea of this talk is to ask a question, are there any other spin models which have Pfaffian correlations? And the answer will be no. So actually, this is only Ising. OK, but let me start with some definitions. So I talked about the Ising model 2 weeks ago, but let's define it again. So it's a probability measure on a space of spin configurations on a finite graph, say connected. So in this talk, I will just denote it with P, and the spin configuration is just sigma. So it's a probability measure proportional to some Gibbs-Boltzmann factor. And in this talk, I will assume that the interactions are nearest neighbor. So we take a sum over all adjacent vertices in the graph. And then I have some coupling constants which measure the strength of interaction. And then there is the product of spins. So sigma here is in plus minus 1 to the power vertices. I don't have a boundary, and I will not have a boundary. But thanks for the question. So some notation for a set of vertices. I will write sigma A just to be the product of all the spins at these vertices. And I will denote expectations with a bracket, sort of the physical notation. OK, so where F is something which F, we call it an observable. So it maps from the space of spin configurations to, say, to the reals. OK, so I state the classical theorem. So it's from 1978. And it's by Groeneveld, first author. So it's not alphabetical, but that's how it's on the paper. Boel and Kasteleyn. From 1978. OK, so what does it say? If G is planar, and my points and my vertices lie on a single face of the graph. Say, I will always assume the external face. So A is a set of even cardinality, because otherwise the correlations vanish by spin symmetry. So if I have, say, V1 up to V2K on a single face, then there is something special that happens, is that the 2K point function, which is the expected value of sigma A, is just the Pfaffian of the 2-point functions. So how do I write it? I write it's a Pfaffian of the matrix of the 2-point functions, sigma Vi, sigma Vj, or say this is an upper triangular matrix. And you can make it, you can extend it to an anti-symmetric matrix, and then just take a Pfaffian, which will be the square root of the determinant. So you can also expand it in a graphical way, which I like very much. So I just like the formula for what it is. So we'll have a sum over all pairings, P, of the vertices. So a matching, basically. It's a splitting in sets of size 2. And then I take a product over all the pairs in my pairing. And then the 2-point function. OK, I forgot something. I forgot the sign. And the sign will be minus 1 to the number of crossing of that pairing, which I define now. So you can think of having a pictorial definition of this Pfaffian, putting V1, V2, say, counterclockwise, okay, V3 maybe, and so on, up to V2K. Then each pairing you can draw as a chord diagram. Okay, maybe we have something which crosses actually. Actually, here cannot be right. Maybe I have something which crosses here. And this crossing is just the number of crossings in this chord diagram.
So, can you explain why this matrix is anti-symmetric?
Okay, sorry.
It must be obvious, but
I just wrote the upper triangular part. So all of these things are positive, and I can just, I can make an anti-symmetric matrix of it. Yeah. Okay. So this is sometimes called the free fermionic Wick law, or yeah. So this is somehow a sign that the Ising model has some fermionic structure. And so far, the proofs of that fact, okay, I know at least 3 proofs. Okay, now we have another proof yet, but so they go either through a dimer representation of the Ising model or through the so-called double random current representation of the Ising model. So these tools are not available for general spin systems. So I will present today a proof which sort of works in some sense for general spin systems. So actually this is 78, but if you think about it, so there is a solution of the Ising model from 66 by Fisher. And if you know that solution, so you just have a dimer model on some decorated graph. And then these boundary spin correlations, you can write them as monomer-monomer correlations on the dimer model. And then the graph is actually non-bipartite, so the partition function is a Pfaffian. And you can convince yourself that this Pfaffian formula actually holds from the dimer representation. But I will not go into that. OK, so that's easy. But so I interested mostly in spin models. So I really wanted to understand since a long time ago why is this true actually. So you can define a larger class of models where I define a probability measure on a space of spins. But now the spins will be just, say, real valued. Real valued. And then what I change in this formula is that, OK, I have to write the density of the measure with respect to some background measure. So what I do is for every vertex, I have some background reference measure, which will be a probability measure on R. I will call it mu V of sigma V. And I change it by looking at this random Nikodym derivative where I bias everything by this exponential. Okay? I call this the classical spin model. There will be another generalization afterwards. So classical spin model. So I took this name from the paper of Bridges, Froelich, and Spencer, which is quite influential from 82. So they consider this class of models. OK. So what is our theorem? Our theorem is the following. So it's sort of the reverse statement of that theorem in the setup of spin models, these classical spin models. OK, so let me have a classical spin model. On G. And I would like to say that there is some special set of vertices where this condition holds. So I will denote this condition by star, say. So there is some special set of vertices, which I denote by W, be such that this condition star holds for any subset of that set of vertices. So in that statement, I can take any subset of even cardinality of A, and it still lies on the same face of a planar graph, so the same thing holds. So I want this condition for any subset A of W for all Okay. And the statement is the following, basically that this is an Ising model on a planar graph. And what I mean by that is that then there exists an Ising model. So I will denote this time by, say, P with a subscript Ising. Ising model on a graph, which for now I just call G prime, but it will be constructed from G. Such that actually this W is a subset of that. So basically from we will have a construction which goes from here to there and doesn't touch W. So this W will always be a subset of these vertices. And W is a subset of V prime. Okay, on a planar graph here. And W on a single face. Face of G prime. And yeah, the last important condition is that all the 2-point functions match. Because if they match, all the correlation functions match by this Pfaffian formula. And such that in the original system, if you look at any 2-point function, it's the same as in this Ising model. For all points in the set W. Okay, so that's the theorem.
You assume G to be planar?
Yeah, so I wrote it here, sorry.
Not G prime. G.
No. So we get both planarity and Ising at the same time.
Yeah. Naive question, what is the background measure for Ising? Is it 2 Diracs and 1 and -1?
Sorry, can you say it again?
The background measure, UV.
Yes, so thank you for this question. For Ising, I can take the 1/2 Dirac measure at -1 plus Dirac measure at +1. And also this red part contains, say, the Gaussian free field, discrete Gaussian free field. So both of these models are, if I put Gaussian reference measures with specific variances which match somehow these coupling constants, I can produce a discrete GFF. Okay.
Isn't there a more general statement that says, what you require?
Yeah.
You don't need any? No.
Yeah.
Given the spin correlations, then you can just construct some abstract graph on which
there is a theorem like that using total positivity results, but the point of this result is that one of the questions you may ask, are there spin models which are solvable, and do the graphs have to be do the graphs that where the spins live have to be planar for that purpose? So okay, I actually haven't finished this statement because I said I finished, but I actually haven't. So I will tell you how to get this graph from that graph. So I think in this way, this is a more. So I wanted to talk about 2 theorems today. You already went to the second one, so that's okay. So what are the moves? Is that in my original graph, if I have something like a part of my graph which is disconnected from W by removing one vertex, I can just forget about it. I can remove it from G. It's the same when I have something which part of my graph which is disconnected by 2 vertices. I can forget about it and put an edge instead of this whole part here. So by this I mean that this part is disconnected by these 2 vertices, and there is a third move which is the same but for a triangle. Whatever I have here and this part is disconnected from W, I can just replace it by a triangle. So the claim is that G prime can be obtained from G by these moves. And it's planar And on that graph, it's only the Ising model. So all reference measures are like that. Yeah.
The meaning of inside when it's not planar?
I mean, just removing, removing these three vertices disconnects some part of your graph from W. So that I just mean that this is the part of the graph. So I just remove it, and I put these three edges connecting these three vertices. Yeah.
With some interactions.
With some interactions, yes.
But isn't there a highly non-planar graph that cannot be reduced to planar by these moves? So how can that theorem be true? Does it say that in such a case W doesn't exist?
Yes. So the Pfaffian structure imposes topological constraints on your graph.
And on the measure.
And on the measure.
Wow.
Because part of the theorem says that in this case the measure has to be the Ising measure. Is that correct?
Yes. It has to be Ising on all the vertices of this graph. Right. So, okay, I haven't given this talk yet, so I apologize if I run out of time. But so this is still work in progress, and I welcome any comments because I expect that some of you know these things better than I do. So, okay. All right. So maybe I just tell you more about the proof that we have, and then maybe mention this other theorem that is proved by some beautiful results of speakers from yesterday. And okay, maybe then I'll stop at that. But all right, so how do I get topological information on the graph and on the measures from the Pfaffian structure? So there is a lemma which I have in one of my papers. I'm assuming this is well known. So, but I haven't found it anywhere. Anyway, it's about Pfaffians, so it must be well known. So what is this lemma? So the lemma says that if star holds for any A subset W, and this is equivalent to the vanishing of some correlation function. And the correlation function is the following. So I have a phi variable, which I haven't defined yet. Sorry, this will be for all. Right, so this statement is for all B non-planar. So I have two things which I haven't defined, so I will define them. All B subset W non-planar. Maybe this is a bad word, but for the purpose of this talk, let's keep it. So I have another variable which is phi tilde, and this is evaluated product over all vertices in W minus B, that this is 0. Okay, and what do these two things mean? First of all, these variables phi are just the sum and difference of sigma. This is sigma V plus an independent copy of my system. So I take two independent copies, and the other one I denote with a tilde, and this one will be sigma V minus sigma tilde V. So this is in statistical physics sometimes called the Genebra rotation. And what I mean by non-planar. So non-planar, I mean the following. So suppose that W has actually 4 vertices. So that's the simplest case. I look at B and I color the vertices of B. Okay, this is wrong color. Suppose I color the vertices of B in red, and I leave the rest white. So I mean non-planar means that there is no pairing of these 4 vertices where red gets matched with red and white with white, and such that the pairing is planar. So here the only such pairing is non-planar because I need to have a crossing. So if I put, this means if I put an insertion of phi here, phi tilde there, phi here, phi tilde there, and if the product in expectation is 0, it actually means that the sigmas on these 4 points satisfy the Pfaffian rule. Because for 4 points, that's the only non-planar set. Yeah.
Does it mean that your set W comes from with the cyclic ordering?
Yes, yes, sorry, yes. Let's suppose it's ordered in some way. Mm.
So in that theorem, is it also ordered, or?
Yes, it is also ordered.
Is it a total cyclic order or only partial?
A cyclic order.
It's a cyclic order. Just imagine putting them on a circle.
Marcin,
Yeah.
the expectation we can put on the right, we said there is like two independent copies,
Yeah.
so it's kind of a double.
It's a double system. It's a double system. So that's I take 2 copies of my spin model. I denote one of them by tilde, but this sort of mixes the two, this rotation. So, okay, so this is non-planar, but so there are also planar pairings where you can actually do that. So this is planar, so this will not vanish. Okay, so this you can prove. It's just using this combinatorial expansion of the Pfaffian, this is quite easy to prove. All right.
So planar means cyclic interval, is that right? Or?
Right, so there is another way of seeing that. You can put sources and sinks. Suppose this is my first point, and suppose I have a rule that if the first point is red, then I put the source. And then if the color changes, then I don't change the arrow. So I put the source as well here. Also changes its source. Also changes its source. So I have 4 sources and 0 sinks, and that basically is equivalent, or the fact that there is a different number of sources and sinks is equivalent to this set being non-planar in this definition. And if I do it for here, suppose I start with an arrow, then I have to keep it like that because the color changed. But if the color is the same, I flip the arrow. And here I have to keep it. So I have 2 sources and 2 sinks.
Non-planar means that there's no planar pairing of the points.
Yes.
Of the points of B and the complement of B?
E and the complement.
Yes.
Okay.
Okay, so how do we get information on the graph from such statements? So now my statement is that for all non-planar subsets, I have this 0 correlation.
Wait,
No, but
is the proof of this lemma supposed to be easy?
I don't know what you mean easy. This is a product. No, you shouldn't see it. No, it's a proof. It's a proof. Yeah. You expand this into. This is a product of sums with signs. You expand it into a whole. Into products of sigma and sigma tilde. You separate the independent variables. They are both Pfaffians. So it says that Pfaffians have some relations, quadratic relations between them, which probably are classical. Okay. So what I want to most talk about is so this is actually a side result of our project, where we sort of study general Edwards-Sokal representations of spin models. So if you don't know the term, then don't worry. And general will mean that they are coupled somehow, in this case. So Edwards-Sokal or FK or random cluster representation. Okay. So sometimes, at least I find it useful to generalize the setup, and then maybe you have new ideas. So the generalization is that I will talk about general spin models. And the difference is that the spin space is just some abstract space S, say. So every spin is in S. And then instead of that term here, I have minus the potential function. So for every edge, I have some potential function which looks at these 2 spins, so sigma u, sigma v. and tells you what is the energy of that configuration. And yeah, abstractly, it can be any function. OK, so this is a general spin model for me. So what are, for us, these representations? Sort of, they are graphical representations of the model, which help you somehow apply the symmetries of the model when maybe you cannot do it for some reason. So what I mean by that is that if I have a mapping, say iota, if I have a map iota from S to S, which preserves this potential function, if I apply it at both coordinates, and my system doesn't have boundary condition, I can basically apply this map to every spin, sort of rotate the system, this whole energy is the same, so the distribution after rotation is the same. So if your Hamiltonian has a symmetry, no boundary conditions, your system is symmetric under that symmetry. But sometimes you impose boundary conditions, and then if you want to apply the symmetry at the boundary, you cannot do it because you cannot touch it somehow. Yeah.
What is S? Is it a subset of R? Or?
No, it's just abstract space, S.
Because you're multiplying the spins?
No, it's a comma. It takes two values, say. OK. All right, so this is the most interesting part, I think, of this talk. So I will not manage in time, but I hope you will remember this construction. OK, so I will be looking at such maps, which are involutions, actually. So suppose is an involution which preserves all the potentials involution. So iota squared is identity. And I assume also that it preserves the background measures. So if I compose my measure with iota, then it's the same measure. You can think of sign flipping, changing sign of a symmetric measure. OK, and I will write the second condition, which is that it preserves all the potentials. So if I have two elements of my space, then if I apply iota, then it's the same. OK, so that's that. And now what do we do with that? We will define a percolation configuration. Given a spin configuration, I will tell you which edges are open and which edges are closed with some rules. So how do I do it? So let me start with a spin configuration. So I will always call it sigma, I guess. And we define omega, which can be thought of as omega iota. And it's a configuration on the edges. It goes from the edges to 0, 1. All right, so what do I do? For an edge, E, which is UV, so two vertices, I look at the value of the potential at that edge of this configuration. So if e to the minus v of that edge sigma at position u, but then at position v, I apply my symmetry. So I flip one of the points. So that's something I cannot do usually, because one of these things is no. OK, so that's something I would like to do, actually. So I freeze this one, but I flip only one of them, but I cannot do it because that doesn't preserve the energy. But if this is actually the minimal of the two possibilities, because, OK, so if this is m, so I define that now. If this is the minimum of the two possibilities, which I mean that it's e to the minus v sigma e sigma v, and the one where I flipped, actually, sigma u iota sigma v. So I call it little m. Then I say that this edge is closed. Then omega at e is 0. Okay. So there is another situation where actually this is the maximum. So otherwise, this thing is actually the maximum. I have an error in my notes. Sorry. So there shouldn't be a iota here. So if your current energy or current weight is the minimal of the two possibilities, one of them is after I flip one of the endpoints, and you see here that the fact that it is an involution, it doesn't matter which thing I flip, because this is an involution which preserves energy. So if I apply I, again, this will preserve. So it doesn't matter which side of the edge I flip, which is an important property of this construction. So otherwise, this thing is the maximum, and I toss a coin. So otherwise, with probability m over m, depending on these two values of spins, where the capital M is the maximum, I declare it closed again. Okay, so with probability 1 minus that, this is open. Okay, so the last case is where I have open. So now I have a sigma and I have omega. So what is the main lemma? The main lemma is that the law of the joint of the couple, the law of sigma and omega, is unchanged by flipping or applying iota to spins in the open clusters of omega. So for every open cluster, I can flip all the spins independently of the clusters. And this will preserve the distribution to all open clusters. All or to one, whatever you do, to all open clusters. Okay. So this is quite abstract. You can think about the spin flip, and then for the Ising model, this gives you just the FK percolation model. And what is the idea? Somehow, if my current weight is smaller than the one after flip, I don't have enough weight to flip it. But if it's the opposite, you know, if the weight is capital M, then I can sort of pretend that the weight is small m by tossing a coin with probability small m over capital M. And this gives me this, so I mark this configuration saying this is the place where I can do the flip. And this gives you some Markov property, which is this lemma. You can think about a very graphical representation of that, very graphical example where you have a Gaussian free field on a graph. Suppose this is an edge. And for the Gaussian free field, it's a real valued field, so it has real values on these vertices. And there is a representation where actually, given the two values, you can sort of define the Brownian motion between these 2 points on this edge. This is called the cable graph construction of the discrete GFF. And then your flip can be, say, reflection through some level, alpha. So I reflect either this part or that part. And then the set of closed edges is the set of edges where this Brownian path actually visits that level. Because if it visits, I can always reflect by reflection principle. So I can always apply this flip. And if it's open, actually it means that it either stays completely below this line or completely above this line. Okay. So This is basically FK representation.
The flip doesn't leave the a priori Gaussian measure unchanged. The flip around 0, yes, but the flip around another line doesn't.
Well, I mean, you have a Markov property of these bridges. So it actually does. I mean, what you see inside is an independent GFF with 0 boundary condition. Okay.
Is the potential effectively symmetric?
Let's assume it's symmetric. Actually, the whole theorem that I stated works for arbitrary potentials V with the property that the second sort of derivative of that thing is negative. If you have a model like that, it satisfies Pfaffian correlations, it's also an Ising model. It doesn't have to be a product of two spins. Okay, so where is this going? I want to have a representation for such observables. So the idea is to take the space, the product space, so S is just R times R. The measure at the vertex is just the product of the two measures. So I don't know, I can denote it with a bar. This is just the product measure. And the potential is just the sum of potentials. So VE of, now I have S bar, and T bar at an edge. I have two copies of every variable. So I say that this is minus because in the definition there is a minus before the potential, and the sum of ST plus S tilde T tilde. Okay. What involutions of that system are very natural? So it's a map now from this product space. So I want to take one involution which just reverses the points. So S tilde S. So it's an involution. You can check that all conditions of my framework are satisfied. And then I say that kappa is minus that involution, which is also an involution. Kappa is minus iota. Okay? All right. So why are these relevant for these fields? One of them changes one field to a minus but doesn't touch the other, and the other one does the same but vice versa. If I exchange the coordinates, this one is unchanged, but this gets a minus sign. And if I exchange and take a minus sign, then this is changed and this is unchanged. Okay? Okay, maybe. So there is another lemma. Okay, I have 10 minutes, so maybe I at least tell you what the new part of our investigation is, that we consider sort of couple FK representations. We want to have an omega for this flip and an omega for that flip. And the point is that these are very nice. We call them orthogonal, and they also commute. And if you have this condition of orthogonality and commuting, you can do all these random choices independently. So I have first my spin configuration. I toss coins for omega iota. I toss independent coins for omega kappa. And after I've done that, I can flip every iota cluster by applying iota, and every kappa cluster by applying kappa independently. And this all preserves the whole distribution of sigma, omega iota, and omega kappa. Okay, so I have this triple. I can do these operations. The law is preserved. Okay, so this is the lemma. I will not write it down. But from that lemma, the following thing, which goes back to where the whole the discussion started, so a corollary, is that if I look at such correlation functions of phi and phi tilde, then this is the same as if I plug in an indicator function here of some event. Because after I've sampled all these clusters, if there is a cluster of iota which has an odd number of vertices in B, I can flip it, and it will zero this correlation because this will flip. So the only event that is left is, we call it, okay, omega iota is in what we call FB, say, means every cluster has an even number of B vertices, and omega kappa is in FA. All right. So where is this going? So this is already some topological information, but this is in expectation. We want to say, when is this actually not in expectation, but almost surely? When do we get some information almost surely? So the thing is that if you check a computation, by the definition, if an edge is iota open, you can check what the condition tells you. It means that that's the last case of the sampling. So it means your current weight is larger than the flipped one. And you actually, yes, and the flipped one is strictly smaller. Because otherwise I would have the edge closed, because the small m over capital M would be 1, and then it's closed. So this actually implies something on the potential of the edges. So if this is open, then actually you can check that after a very simple computation, that you have this condition, sigma u tilde, sigma v minus sigma v tilde, that this is positive. And if this is kappa open, then you have the same thing, but with pluses. Okay, it means that the signs of that function are constant on open clusters. If I have an open edge, the signs of these two things are always the same. So this information carries across the whole open cluster. But then you check, when is it almost surely the case that a vertex cannot be both adjacent to such an edge and such an edge? So it's only when the product of these two things is 0, actually, always. So if I have two edges, one of them is uv and the other one is uv prime. So here I have v prime, say. If I multiply these conditions, I get that the square of sigma u is equal to the square of sigma u tilde almost surely. And they are independent. It means that they must have a constant size, almost surely. It means that they must be an Ising model. So an Ising model tells you, if you have an Ising model measure on a vertex, it means that two paths which are open in one and the other percolation, they cannot go through that vertex. Almost surely, and this is if and only if. Okay. So also this property tells you that here everything is positive. Because they are connected, these vertices are connected by open paths in even sets. So all the contributions of signs are the same. So it means that this thing is always positive, which is the link with total positivity, because actually if you have a planar set B, if this is B and this is W minus B, then this would be a determinant of a matrix, not 0. And that's the other proof that I will not talk about. But the property is now that this is positive, but it has topological information. And we want these things to be 0, which means that this is almost surely satisfied. Like, okay, this is almost surely not satisfied. So you have almost sure information on the graph. And this is only in the case of the Ising model. So that's the representation. You can apply it to other systems. But so what is our proof now? So we just go by induction. Say you take 4 points. You assume they have a Pfaffian correlation. It means that you have this configuration which is non-planar on your graph, which means that every path. So you have 4 points. I draw them on a circle, but it's not on a circle in the statement. The conclusion is that they are on a circle, basically. So you have this non-planar coloring. You know almost surely every path which connects that 2 vertices crosses every path which connects these 2 vertices. And actually, it has to cross it at an Ising type vertex, because otherwise it can actually, you have a positive probability of crossing, because that thing will be, this will be positive, or this thing will be positive. So by induction, we apply these moves, these 3 moves, which work well with the Ising condition and with the condition that these paths must intersect. If you apply these moves, both conditions are satisfied in the graph that you obtain after the move. So this is sort of a combinatorial part of the story. So I have 2 minutes. All right. So I proved that this thing is non-negative, right? So actually, there is a class of distributions which are called Ginebra distributions, for which something like that, the definition is that a vector of sigmas, a random vector sigma, is a Ginebra distribution if you take like a double system and you look at all these possible products of sigma plus or sigma minus sigma tilde, that they're all positive. So this is a very important family of distributions for the Ginebra inequality in statistical mechanics. And with this argument, we get that for planar colorings, these things are strictly positive and they are determinants. So we have this total positivity condition satisfied. And then we can prove that there exists an Ising model with the same 2-point functions, just using your result, the result of Galashin and Pilyavsky. So, okay. It is a stronger result because the assumptions are stronger, but somehow here we have a sort of this probabilistic proof with a, really explicit construction of G prime from G. I'm not sure if the other proof gives the same thing. So that's one of my questions. And the other question is that this is positive only if all the coupling constants are positive. So the Ising model satisfies Pfaffian relations irrespectively of the coupling constants. So there is a question, what if you don't have positive coupling constants and you have Pfaffian relations, is there always a planar Ising model with these correlation functions? I don't even know what to expect. I think it's not the case, probably. Because these expectations would be signed, and then you have no topological information, because you can have cancellations which lead to 0. So here we don't have any cancellations, basically, in this formula. That's why we can conclude. OK. Well, yeah. Thank you very much.